Hello everyone, welcome to my dissertation defense. My name is Khurram Soomro, my advisor is Dr. Mubarak Shah, and the title of my dissertation is Online Supervised and Unsupervised Action Localization in Videos. So first I'd like to start with defining the problem of action recognition. So the way the action recognition works is that given several videos of human activities, human actions, the task is to learn a classifier that can label each one of these videos, such as shown over here. So let's say if the human action is diving, lifting, golf, swinging, bench, walking, you learn a classifier that can label each one of them from a set of labels for that particular data set. Now, the task of action localization is a bit challenging, where not only do you need to recognize what the action is in a video, but you also need to detect where the action is. Now, this action detection can take place in two ways. First, you can do it in trimmed videos, which means that the videos are shortened to the length of the action itself, where the video starts where the action starts and ends when action ends. And in that kind of videos, you mostly do spatial localization by putting a bounding box. As compared to untrimmed videos where you can do either temporal localization, which is start defining the frame, the starting and the ending frame of the action itself, or it could be spatio-temporal, which means you're defining the starting and ending frame as well as the bounding box in each one of those frames. So here is an example. So given these human activity or human action videos, we want to detect by putting a bounding box as shown over here, the yellow bounding box, and then also recognize them by putting a label. Now, there are a number of challenges for action localization. For example, in action videos, you can have cluttered background, which means that if you're trying to detect an action, there could be several other players over here where the action is basketball dunk, or there could be several hundred people in the audience, and it becomes very challenging to identify where the action is in this kind of video. Or you can have multiple actors or actions being performed simultaneously, such as shown over here in salsa swing. Additionally, you can also have untrimmed videos where you don't necessarily know when the action would start. For example, in this, the intended action is hand waving, clapping, or boxing, but it could start anywhere in a long video, and the same person can do multiple actions one after the other. Now, there are a number of applications to action localization. For example, you can use it to search in a video. When you know the action, you can use the features to learn an action and then search in a video. You can use action localization to retrieve actions, as well as perform human-computer interaction, where the computer understands what the human is doing and then try to respond to those actions. You can also use it for autonomous driving, where a car can automatically detect what a pedestrian is doing, whether walking or running, and then perform, behave or takes necessary precautions based on that. Lastly, it can also be used for general video understanding, whether you can use it for video captioning or and so on. Now, there are a number of ways to do action localization. For example, you can do it in an offline manner or in an online manner. To compare these two, in offline, usually you have the entire video available, where you have the entire video, all the frames available to you, and then you want to detect by searching in the entire video. As compared to online, where you have only partially observed video in a streamed video. So you have only a bunch of frames, or maybe one frame, and you want to detect where the action is and what the action is. Hence, you have the entire motion available to you, which can be used by a classifier to recognize and detect an action, as compared to you have limited motion information when you have a streamed video in online sense. Hence, it becomes an action recognition versus a prediction problem, right? And lastly, because you have all the frames available in offline, you can use all those frames to detect pretty much by searching everywhere, as compared to online, where you have to do detection and prediction on a frame-to-frame basis. Another way of performing action localization could be in a supervised versus unsupervised manner. Now, the way that supervised works is that someone has gone through the effort to label all those videos and tell which action is being performed in that particular video, as well as annotating all those frames by putting the spatial bounding box, as well as defining the temporal boundary of those actions. In comparison, unsupervised action localization doesn't assume any such information. So you have no video level labels, you have no annotations, and the task is given a set of videos, you need to perform action localization. Moving on, this dissertation is divided into three parts. First, I'll talk about supervised localization, where we'll be using context walk to come up with an efficient way of localizing actions. The second part of the dissertation is online localization, where we are the first to propose an online method to localize actions in a streaming video, where we not only detect actions, but we also detect interactions. Lastly, the third part includes the unsupervised localization, where we also are the first to propose such method, and we automatically discover actions by clustering those videos as well as localizing them by putting a spatio-temporal bounding box. So let's move on to the first part, the supervised localization. So this work is called Action Localization in Videos through Context Walk, and this was published in ICCV 2015. So the motivation behind this work is that many of the existing solutions to supervised action localization work in the way that they use some low-level or high-level features to learn an action detector. And then after they have learned this detector, they'll exhaustively search in the video, which means spatially, temporally in each frame, as well as in time at multiple locations and scales. Now, if those kind of videos are large, which is those videos are untrimmed, long videos, or high resolution, it becomes really impractical to search everywhere. And you can't really scale such action detector to a large extent. Hence, in this work, we propose an idea where we want to come up with an efficient way to localize actions. So the key idea goes like something like this. So let's say we have an action video, and here I'm showing a few frames from that video where the action is diving. We divide this video into some video regions based on their low pixel values and come with these Supervoxel regions. So once you have these regions as well as the ground truth for that particular video, we learn contextual relations between the background as well as the foreground action. Now, these relations are 3D displacement vectors, which tells us that given a particular location, where is the action placed relative to its background as well as relative to within the human body parts of an action. So they can be divided into two parts. First is the action to scene relation, which is coming from the background to foreground, which is pointing out, let's say, if there's a diving board or the swimming pool, where do you necessarily think the action would be for diving in that case? Or it could be within an action itself, where you're using some body parts, let's say head or shoulder, the torso or the legs, to point out where the action is in terms of those regions. So that's the basic idea behind this approach. So hence we propose an efficient localization approach where we're trying to reduce the search space by coming up with few possible candidate locations, and then based on that we localize the actions instead of looking everywhere in a testing video. Hence that reduces the few number of evaluations and improves the efficiency of the algorithm. So in training set videos where we have a number of videos and the labels, we build context graphs. So we divide a training video into these Supervoxel regions, and we also given the ground truth. We come up with this directed graph where the nodes are the Supervoxel regions and these edges, directed edges, are the 3D displacement vectors that come up from all the voxels or all the nodes in this video to all the nodes within the ground truth. So here the ground truth regions are shown by the green contour, all those nodes that are within the green contour. So we build this directed graph for all the videos, all the training videos for every particular action. And we call combination of these graphs as composite graph. And we'll be using this information, this context information, to localize actions in testing videos. Now, the proposed framework for context walk in testing videos goes something like this. So given an unknown testing video, where you don't necessarily know where the action is, you don't necessarily know what the action is, you divide this video into Supervoxel regions, such as shown over here. You extract those Supervoxel regions as well as their features, and then you build an undirected graph. Now, in this graph, all those nodes are Supervoxels, and these edges are connected between spatio-temporal neighbors of all those Supervoxels. Now, once we have this undirected graph, we select a node, any node randomly to begin with. That's just like initialization step. So we select a node, and then we use that particular node and its features to retrieve k nearest neighbors from our composite graph that we built in our training videos. So we come up with these nearest neighbors, and using those nearest neighbors, we project displacement vectors onto our testing graph. So these displacement vectors are telling us that given these features, given this location in our testing video, where do we think the action is in space as well as time of that particular testing video. Now, once you project these displacement vectors onto our graph and the video, then we can come up with this conditional distribution, which tells us that which are the more likely or more probable locations where the action is present, such as shown over here. So the more red regions there are, that shows that it is highly probable that that's the action, and more blue means that is most likely the background or non-action. Now, once we have this conditional distribution, then since it's a walk, so we perform this context walk where we go from one node to the other, and we are only evaluating a few nodes in this graph to come up with this accumulation of distribution. probability distribution. So here, given that supervoxel that we selected, we select the next one based on the region or the voxel or the node that has the highest probability. So that is the next step of our work. Once we have that, then we repeat this entire process where we retrieve neighbors, project those displacement vectors onto our graph, and accumulate all those confidences. Once we have that, that's what we call the context walk on our graph. Now, once we have this conditional distributions all summed up, then we use CRF to label all those supervoxels and then come up with this fine action contour to localize the action. And once we have this localization, then the SVM, the classifier that we learned in our training videos, we use that to classify or recognize what the action is. And in this case, it's diving, so it will label this as diving action. Now, we go on to the details of this method. So first, to retrieve all those nearest neighbors, we use the similarity function, which uses the features of the voxel or the node in the undirected testing graph, as well as the features that were from the composite graph in the training videos. So based on that, we come up with a similarity function that retrieves the nearest neighbors. Next step, for our displacement function, which displaces those 3D displacement vectors, we use this function where we have the displacement from our nearest neighbors, and then we use them to project onto each node in our testing graph. Next, we use a conditional distribution, as I mentioned, and that conditional distribution accumulates the displacement function as well as the similarity function to come up with a score for each node in this graph. Once we have this conditional distribution, then we perform this context walk, where we're using the conditional distribution from our previous step of our context walk, and then we add it to the next step of the context walk, as is shown over here. And this function is a weighted decay function, where we give more weight to the present step, and then we add it as we go on. Now, once we have this distribution, our next step is selected based on maximizing or selecting the node that has the maximum probability or maximum value, and that is our next step. And then we repeat the step for a few steps, and then that gives us the detection. Now, the context walk gave us a basis to give us a score for each node. Apart from using the context information of these 3D displacement vectors, we have another way of giving a score to each voxel based on its features itself. So for that, we compute something called the action specificity. So let's say we have these training videos, and each of those nodes is a voxel, and the green bounding box is the ground truth. We cluster those supervoxels from training videos, such as shown over here. Once we have these clusters, we come up with a way to assign a confidence or a score to each cluster, which says that what is the percentage of each cluster that belongs to the foreground. So that when we use the features from the supervoxel in the testing video, we can assign it to one of these clusters and say if it is assigned to one of those clusters that is from the foreground, then it is highly likely that this particular node in testing video also belongs to the action itself. Right. And this is the way that we compute the action specificity, where we use the features from the cluster center and the features from the node itself, and we compute the distance. Now, our next step is to infer the action location using CRF. So for that, we define a unity potential that is based on two things. First is the action specificity that I just mentioned, and the other probability comes from the context walk. The binary potential is based on feature similarity between neighboring nodes, as well as the similarity between the size, and so on. And that gives us the function for CRF that we minimize to be able to get those labels and give us the action detection, as shown over here. Now, for our experiments in this approach, we use improved density trajectory features. We use top 20 nearest neighbors. So in our composite graph, that could have several hundreds to thousands of supervoxel nodes. But for computational efficiency, we only use 20 nearest neighbors to retrieve and project those displacement vectors onto our testing graph. For our context walk, instead of looking everywhere, all the supervoxel regions or all the locations in space and time, we only use t is equals to 5 steps to be able to localize and come up with an action location or action detection. That basically improves the overall computation time to be able to get to the action in a faster manner. Now, for data sets, we tested on 3 data sets. We have UCF Sports, sub-GHMDB, and TUMOS 13, which is a subset of UCF 101. So first, I'm going to show qualitative results on UCF Sports. Here, our detection is shown by the yellow contour, and the ground truth is shown by the green bounding box. And as you can see, because we use supervoxel regions and merge them using CRF, we come up with these fine action contours that gives us the label of the action at each pixel location in this video. The UCF Sports has 10 actions, and it's fairly challenging based on its articulation of actions and so on. Next, we show results on SubJHMDB. This has 12 actions, and they are a variety of actions different. Some are sports actions, some are non-sports. You can say some from gym exercises and so on. Next, we show results on TUMOS 13. Again, the ground truth is green bounding box, and the action detection is the yellow contour. This is by far one of the most challenging localization data sets, which has about 24 actions and about 3,000 videos. So we perform very well on this data set. Moving on to quantitative analysis. So first we show results on UCF Sports. So the way that localization results are shown on these action data sets is that we plot the ROC curve, which is true positive rate versus false positive rate, and at a particular overlap threshold with the ground truth. And then we compute this ROC curve at multiple overlap thresholds with the ground truth, as shown on the right. So first I'm going to show the state-of-the-art results on these data sets. And then this is our proposed approach, where we get better results than the state-of-the-art. And we think that we get this improvement because we are only evaluating at a few locations, and that basically reduces the false positives that we could encounter had we searched everywhere in the video. Next, we show results on SubJHMDB. So here are the state-of-the-art results, and the red curve is our proposed approach, where we perform better than the state-of-the-art results reported on this data set. Lastly, we show results on TUMOS 13. Now, for this data set, we were the first one to report on TUMOS 13. So we came up with a baseline, a supervised baseline that would generate exhaustively bounding boxes in each frame and then connect them based on their features. And this is a baseline for that particular data set, and we significantly improve the performance on this data set, where we perform better at multiple overlap thresholds with the ground truth, going from 10% until 60%. Now, we would like to perform some sort of analysis where, so we propose that we come up with an efficient localization approach. So looking at the state-of-the-art, so there are two state-of-the-art approaches. First is the SDPM, which is a spatial-temporal deformable part model. In testing video, it searches everywhere. So it looks at all possible locations, X and Y, in a frame, as well as time. And lastly, multiple scales, because an action could be of varying length and varying size. The next state-of-the-art is the action tubelets, which builds a hierarchy of supervoxels and then merges those at each level and then come up with these different levels that it can evaluate the action detector. And that has a complexity of n squared, and the first one has a complexity of n4. In comparison to that, because we only perform this context walk at a few locations, which is only 5 in our testing case, with an application of CRF, we perform this localization in a constant time. So in summary, we came up with an efficient way of localizing actions in a supervised manner. We used contextual relations between these different supervoxel video regions, and we performed context walk to localize these actions in testing videos. Now, there are a number of limitations to this approach. Firstly, because all these previous approaches localize action after an activity has occurred. So mostly all of these approaches are offline, which says that you look at the entire video and then you say where the action is, what the action is. Now, this kind of approach cannot anticipate actions. So let's say you have a surveillance video where you want to detect an action right when it occurs or before it can occur. So we can't necessarily do any timely localization of actions, which is very important in case of any alarming situation. So next part of the dissertation would focus on online or an online way of localizing actions in a streaming video. So online localization and prediction of actions and interactions. This work was published in CVPR 2016 as well as PAMI this year. So the way that we define this problem is, let's say we have this video shown on the left where we want to detect and predict the action given by the yellow bounding box. Now this is the streaming video where we only detect and predict per frame. On the right, I'm showing all the prediction scores for this particular action sorted based on the prediction score. The action here is kicking a ball, and I'll play this video and you can observe how the prediction varies with time. Now, as you observed, once we are looking at all these frames with time, we get more information, and that improves the prediction score as we go along. So hence we saw that the kicking a ball, earlier it was lower, then when we saw more of the video, it gave us more confidence and we were able to better predict what the action is. So the way that this problem is defined is that in online action localization, we want to simultaneously perform detection as well as prediction in each frame as we go along, as compared to offline where we had the entire video available, and then we'll search everywhere to detect the action, and then finally use a classifier to recognize or classify this action. Now, the idea in this approach is that we want to distinguish the foreground action from the background. To do that, there could be a number of ways. For example, you can apply human detection to detect all the humans in this video. You can apply some sort of segmentation, either based on object, motion, or more recently, action proposals to get an idea where the action could possibly be. And lastly, you can also use human pose estimation, where you localize or detect each one of those human body joints. For our approach, we combine segmentation with pose estimation to come with a way to distinguish the foreground from the background. So our proposed framework goes like this. So given an input stream of video frames, let's say from t minus delta to 3 frames, we want to detect and predict the action in the current frame at time t. And we do this in a batch of frames. So we use the past delta frames to be able to detect where the action is. So we use the recent information, the features, the pose, and to be able to detect the action. So at each frame, we extract superpixels, which are the small regions, small contours shown in each one of those frames based on similarity of pixels in local neighborhood. We also extract poses, that's the human body joints shown over here. And since these poses, we use any underlying pose estimator, the way that this pose estimator works is that it detects the pose in each frame without any temporal notion. So these poses can be some error sum. So next step is to combine these two together. So the first component of our approach is superpixel-based foreground likelihood, which is the way to estimate where the foreground is. Next is pose-based foreground likelihood, and then we combine this to come up with the location of the action. That's the goal, to tell where the action is at time t. The third component of our approach is state transition model, which says that given the location in the past few frames, can we use that location information to tell where the action could possibly be in the current frame? And that's the state transition model. We combine all these three components in a Bayes rule formulation, where we try to get the probability of the action of the location where the action could be based on all the superpixels as well as poses from the beginning till time t. Lastly, the state transition model, in this case, we assume to be Gaussian distributed, going from one frame to the other one. So first, we look at superpixel-based foreground likelihood. So given all these superpixels as well as pose bounding boxes in each frame, we learn an appearance model, which says that what is the most likely appearance of this particular actor performing the action, so that we can look for that same person in the next frame. So the way that we do that is that we have these superpixels, we cluster them together based on their appearance, and we assign a confidence to each one of those clusters based on what percentage of this cluster is belonging to the foreground. And then we can use that as an appearance later on to generate a heat map or a confidence map such as shown over here, which says more red it is, more likely that this is the action with the same appearance of the actor, and blue says that it's most likely from the background. Now, this appearance model is updated every 5th frame because we want to have the most recent information of that particular actor, and because these actions have high pose variation, it's important to have the most recent appearance of that particular actor so that we can localize in a better way. Next, looking at pose-based foreground likelihood. For pose-based foreground likelihood, as I mentioned, that since we use a pose estimator that detects these poses in each frame individually, there could be some errors in localizing all those human body joints. And what we do over here is that we want to refine those poses that we can use the temporal information to come up with better poses. So for that, we impose some smoothness constraints. So it uses all those human body joints in each frame to fit a spline trajectory. And based on that, we look at the appearance of human body joints, the location, as well as the scale of pose to reselect poses that are better aligned temporally. Looking at pose-based foreground likelihood, this is how we define the cost function. So our cost function looks at the raw cost of each pose. So we can use any underlying pose estimator that gives us a score or cost for that particular pose estimated in that particular frame. Apart from that, we come with 3 components. So we have the raw score, we have the appearance, we have the location of the human body joints, as well as the scale of the pose. Based on all these 3, we define this minimum cost function, and we minimize that to reselect poses, which is given by P star over here. These new poses are iteratively selected, which are more aligned with one another in a temporal sense and have better human body joint locations. So the first part is the appearance smoothness of joints. So for appearance smoothness, we look at the superpixel-based foreground likelihood score for each human body joint, and we see how similar it is across those frames. So because we want the appearance to be similar within a short temporal window, this is how we compute the appearance smoothness. Next, we look at the location smoothness of joints. So since we fit a spline trajectory through each one of these human body joints, let's say we have 15 human body joints, we fit 15 trajectories as shown over here. For each one of those trajectories, we want the trajectory location, the estimated trajectory location of that joint, as well as the actual human body joint location in that particular frame. We want them to be as close as possible. Hence, we want to minimize over this cost function. Lastly, we want the scale of the pose to be smooth, so that we don't want any drastic changes in human pose in a small temporal window. So we define the scale smoothness where we have a bounding box or a scale for the trajectory locations as well as the pose itself in that particular frame. And then we look at the difference and we want to minimize that they're as close to one another as possible. So here are some qualitative results for pose refinement. So here we're showing two actions, kicking and walking. This is before we did pose refinement, and this is after we did the refinement. In this, you can observe that in the left, in kicking action, the left arm wasn't correctly localized. So after refinement, we're able to correctly localize the arm, which is the elbow and the hand. On the right, we show that there were some error in the head location of the person, and we're able to correct that. That gives us some pose improvement, and that helps us in localizing the action. Once we have the superpixel and pose-based foreground likelihood, we build a spatio-temporal graph where all these superpixels are nodes, and the edges are connected spatio-temporally between all those superpixels within a frame as well as superpixels across the frame. Once we have this, then we use CRF to localize the action, where we select the supervoxels that belong to the foreground based on the superpixel and pose-based foreground likelihood, and that gives us a fine action contour as shown over here. The unity potential for CRF comes from the superpixel and pose-based foreground likelihood, and the binary potential comes from similarity of color between superpixels, motion, as well as edges between those superpixels in all these frames. So for CRF, as I mentioned, so this is a formulation where we have one unity potential and two binary potentials, which is the spatial smoothness as well as the temporal smoothness. Since we have this spatio-temporal graph, we have spatial connections within a frame as well as temporal connections across the frame. So we have two binary potentials. For unity potential, we have the superpixel and pose-based foreground likelihood, and for spatial and temporal, we use the histogram of flow. We use the color features of the superpixels, the mean color, the motion boundary, that is the optical flow, and then the edges between those superpixels in space. And then in time, we have the color, histogram of flow, as well as the mean. Now, once we have detected this action using CRF, our next step in that particular frame at time t is to predict what the action is based on its location. So we perform action prediction based on two approaches. So first approach, we learn binary SVMs, and we use those binary SVMs along with dynamic programming approach to accumulate scores in testing video. So in training, what we do is that we have a lot of videos for each action. So we divide each video temporally into 1 second segments. So we have these segments from 0 to 1 second of that video, 1 to 2, and so on. And we do that for each video of each action. And then we learn a binary SVM for each one of those segments. So let's say the video was divided into 5 segments, then we'll have 5 SVMs, 5 binary SVMs for each action. Now, when we have a testing video where we're trying to detect as well as predict the action, we accumulate the scores and apply those SVMs temporally on a short window frame, and then we accumulate the scores based on dynamic programming. And that gives us the action prediction score for that particular video. Now, our second approach, we come up with a second approach that uses structural SVM. And the key idea over here is that as we saw in the first video that I showed for action prediction, we saw that the action predictions improves over time. That's the notion that we use the structural SVM, where we define structural labels that learn the action in a way that the prediction score improves over time as we get more information in the video. So in training, we divide this video into, again, temporal segments, but this time we divide them from overlapping segments. So from 0 to 1 second, 0 to 2, and so on, such that for each, we come up with a prediction score, and then that improves over time. Now, in comparison to the first method, this approach learns only one structural SVM for each action, as compared to those binary SVMs. We had several binary SVM that was computationally expensive, and we had several applications of SVM. So in testing, once we have these locations and frames from the video, we apply this structural SEM at each location, and that gives us a prediction score over time. In summary, this is how our approach looks like, where we started from an input stream of video frames on the left. We use superpixels and poses to come with a way to learn appearance and come with a foreground likelihood score. We refine poses, and then finally we use CRF as well as the structural SEM and binary SEM to predict and localize the action. Now for experiments, we used a number of features. For superpixel, we use the slick superpixels method. We use the convolutional pose machine, which is a deep learning method to estimate poses. We use dense trajectory features and some pose features that were based on human body joint locations, trajectories, and so on. For evaluation, we perform the same evaluation metrics, which is the ROC curves and the AUC curves that we used in the previous part of the dissertation. However, because this is online action localization and we have the notion of time, we come with two new metrics that use time as a way to measure the accuracy. So we define a prediction accuracy versus the percentage of action or interaction that we've seen in the video, as well as the area under curve that gives us the evaluation metric for localization as a percentage of action and interaction observed. Lastly, because we're the first people to propose this problem, we come up with a baseline approach where we exhaustively generate bounding boxes and we connect them in time in an online manner based on their features. For experiments, we perform our experiments on 4 action data sets, JHMDB with 21 actions, sub-JHMDB 12, UCF Sports 10 actions, and then MSR2, which is untrimmed and has 3 actions. And then we also perform online localization on 2 interaction data sets, which is TV-human interaction and UT interaction. So here are some prediction results for our approach. So here I'm showing the foreground likelihood score on the left, the frame of the video, streaming video in the middle with the localization shown by the yellow bounding box, and the prediction scores on the right. So the action here is kicking a ball, and as you observe, we are able to predict what the action is before the actor even kicked the ball in this video, which is because we are able to use poses, and that particular pose for that particular action gives us a cue to be able to predict that action. Here's another example for catching. Again, we have the foreground likelihood on the left, the detection, and the prediction on the right. So this establishes that using more information as we go along in a video, we are able to better predict with time. So here are some qualitative results on UCF Sports, where again, the action detection shown by yellow contour and the ground truth is shown by the green bounding box. And we're able to localize multiple actions simultaneously and correctly localize by labeling each pixel for that particular action. Here are more results from JHMDB, which has 21 actions. Now these were the action data sets. We also show results on interaction data sets where we have multiple people interacting with one another. Here is results on UT interaction data set. So we have 2 people on the left. We have a person kicking another person, punching, pushing, and then pointing. So here again, the green bounding box is the ground truth, and we're able to correctly detect and predict what the action is. Lastly, we show results on TV-human interaction, which is a data set collected from TV shows, as shown over here. And this is temporally untrimmed, and we are able to detect and predict what the action is over here, where actions vary from subtle actions such as hug, handshake, and so on. Now, moving on, we look at the quantitative analysis. So as I mentioned earlier, that we want to analyze the prediction of interactions and actions with time. So here we show our results on all these 6 data sets, where we have 2 proposed approaches. We have the results on the binary SEM with dynamic programming shown by the blue curve, and then the structural SEM shown by the red curve. And in general, we observed that structural SEM perform better on all these data sets because the way that we define these structural labels is that we define it such a way that we want the prediction score to improve over time, and that really helps in predicting the actions in these data sets. Next, we observed since we look at the prediction of all these data, of the action and interaction in these data sets, we can also perform some analysis based on each action or interaction in these data sets. So here we are looking at all these actions from sub-JHMDB, which has 12 actions. We can observe which actions are easier to predict and detect as compared to the others. So we can sort these actions based on the area under the curve, and then find out which actions are more challenging as compared to the others. So in this particular data set, we observed that pushing is easier because it's mostly upright. Poses are easy to estimate as compared to catching, which involves diving, jumping, and so on. So there's a lot of pose variation, and that can drops the performance in this case. Next, we'll also look at interaction prediction, where we show per interaction results on TV human, and here are the results on different interactions. There's handshake, hug, and so on. So here we observe hug is the most easiest one. It's mostly upright as compared to kissing, which is challenging because it's a more subtle action, and we didn't see much motion in that kind of action interaction stuff. Next, we observe that we found the actions which were most challenging or more easy. However, we also want to see how much of the video do we necessarily want to observe to be able to predict the action. So here we set a prediction accuracy, an arbitrary number, let's say 30%, and based on that we say which ones are easier and need only few frames to observe to be able to predict. So here GHMDB has 21 actions, and we observe that shooting ball or shooting gun or pull-up only need a few frames to be able to predict as compared to standing, running, or swing baseball, which needed more frames or more of the video to observe and then be able to predict what the action is. Some of the actions don't have a number, which says that they were more challenging and they didn't even reach a prediction accuracy of 30%, which shows the challenging nature of online action localization. Here are some more results on SubJHMDB and UCF Sports, where kicking or lifting, because it's related to the pose, we are able to detect only based on a few frames as compared to swing side, which has a large pose variation, and we need to observe almost entire video to be able to predict what the action is. Next, we show results on the localization with time. So here we draw AUC, area under the ROC curve, and here we are showing the curve against the action observation percentage or the interaction observation percentage. Each one of those curves shows the overlap with the ground truth. So in the top left, if we observe for GHMDB, the red curve here shows that it has an overlap of about 60%, which makes it more challenging to detect as compared to when it is localized at only 10% or 20%, which is a higher number. And that's the general trend we observed. The performance drops slightly when we have a higher overlap threshold with the ground truth. Now, finally, because we were the first to propose this online localization method, we also want to see how we test against the offline methods, the offline state-of-the-art methods. So here are results on all these 6 data sets. On the left, we're showing GHMDB top left, and then we have UCF Sports. We observed that we perform competitive to the state-of-the-art. In some cases, we perform better than some of the offline methods on UCF Sports at multiple overlap thresholds. And in other cases, we perform competitive to the state-of-the-art offline methods. So that gives us an encouraging way to see that these online action localizations can really work, and we should pursue this. So in summary, we propose a new problem which simultaneously predicts and detects these actions in a streaming video. We use high-level poses and mid-level superpixels to compute the foreground likelihood. And then we used CRF to infer the actions, and we performed a detailed analysis of the online localization versus time. Now, there are a number of limitations for this kind of approach. First, all these approaches that we mentioned in the first part, where we came up with an efficient way to supervised action localization, as well as the online localization, all these are supervised approaches, which needs someone to manually label all these videos in training, as well as annotate bounding boxes per frame. Now, that kind of work is very tedious, takes a lot of time and effort to be able to come up with all these annotations. So it becomes really impractical when the number of classes grows to a large amount, or we have videos that are of longer duration. So recently, people have proposed a data set of millions of videos, so that becomes really impractical and cannot be scaled to this extent. So it can also lead to unwanted biases and errors, because every person might have a different or subjective opinion about defining where the starting and ending of an action is. So this takes us to the last part, or the third part of this dissertation, which is unsupervised action localization. This work on supervised action discovery and localization in videos was recently published in ICCV this year. And the way that we define this problem is that it has 3 problems that we need to solve. First, given an unlabeled, unannotated set of videos, we want to discover the actions and cluster them in training videos so that we can learn an action detector to test in testing videos. Next, we want to annotate all these actions in training videos, which means that we want to come up with a bounding box location and define where the action is so that we can learn a classifier. And lastly, once we have these annotated labels as well as bounding boxes, then we can localize actions in testing videos. So these are the three components of the last part of this dissertation. So the proposed approach, as I mentioned, that we are given a set of unlabeled videos, which has multiple actions, no labels for each video, as well as no annotations. And then our task is to come up with these action clusters, or discover these actions, such that each cluster belongs to a particular action class. Next, we also want to annotate all these videos by putting a bounding box, as shown over here, the yellow bounding box. And lastly, using these two information, we come up with an action localization method to localize actions in testing videos. So first, I'd like to explain the action discovery or the clustering part, where we come up with a discriminative way of clustering these videos and come up with these discovered actions. So the way that we start is that we want to discover these clusters based on an unlabeled set of videos. So here, we want to cluster these set of videos into K classes, where K is known, and that is set to the number of actions for this particular data set. So we start with extracting some features for all these videos, and then we apply spectral clustering. So that spectral clustering gives us an initial clustering for each one of those videos. Next, we build an undirected graph from each one of those clusters and apply dominant set. Now, dominant set is key to this approach, and the way that I can explain dominant set is that it has high homogeneity within the selected subset from each one of those spectral clusters, and inhomogeneity outside that particular cluster. And that basically says that within these all clusters, spectral clusters, we select good videos that we can use to refine these clusters and come with a better action discovery approach. So once we have these dominant sets selected from these spectral clusters, we group all the non-dominant sets that are left from the remaining clusters into lambda, as shown over here. Now once we have this, then we come with an iterative approach where we learn an SVM classifier over here. And this SVM classifier would use the dominant set from each class as positive examples and dominant set from the remaining class as negative examples, and come with a classifier that discriminatively selects from the non-dominant sets and adds to the cluster itself. That is a way to refine and improve the clustering, and hence we get better action discovery results for that. So once we have these discovered clusters, and we assume that each cluster belongs to a particular action, we want to annotate, and for the annotation, we come with a variant of knapsack approach. So first, I'd like to define what knapsack problem is. So for a 0-1 knapsack problem, given a set of items, so let's say we have multiple items shown over here. Each item has a value. Let's say this one has $4 and has a weight, which has 12 kg in this case. We want to fit these items in this knapsack or a bag such that we want to maximize the value of items in this bag. However, we are limited by the total amount that we can put in the bag that is dependent on the weight of the bag, which is 15 kg. So we use a similar analogy. So for our annotation purposes, we have, let's say, this training video, and we divide this training video into supervoxel regions. So the analogy goes like this, that we have these regions, and we treat each region as an item, and we want to select these items such that we can come with an approach to merge or select these supervoxels that belong to the action. So once you have the supervoxel regions, we compute a value for each item, for each supervoxel. That is an action distinctness score. That tells us how likely it is to belong to the action. And then the weight of that particular supervoxel is the volume occupied in the video, which is the accumulation of the pixels in that particular supervoxel. Once you have this knapsack value and weight, then we define or construct a directed acyclic graph shown over here. Now this graph is a temporal forward-flowing graph where we have two dummy nodes, a source and a sink, and we connect these nodes from the start till the end of the video based on the supervoxels. Once we have this, then we define some temporal constraints, which say that although in a knapsack, a 0-1 knapsack problem, we can select items that have the maximum value. However, that doesn't necessarily guarantee that all those items selected would give us a contiguous or continuous action in this video. So for that, we impose some temporal constraint that ensures that the items that we select are temporally connected from the start till the end of the action. So once we have these constraints, then we apply knapsack, and that gives us a group of supervoxel nodes that we select to give us the action localization as shown over here. Now this approach is repeated a number of times to get multiple annotations in videos, because each video can have multiple actors, as I mentioned before, that can be performing the same actions or different actions, and we use Knapsack multiple times to get all the possible annotations that we can use later on for action localization. Now once we have this, then we can get a group of supervoxels belonging to the action, and that is the action annotation for this particular training video. Now, moving on, first I define the knapsack value. So given a video, as shown over here, a diving video, we define the knapsack value based on 3 components. So first is humanness, next is saliency, and the last is motion boundary. So the way we define the humanness is that we apply a human detector. So we apply phosphor or CNN in this case to each frame, and then we look at the overlap of all those bounding boxes with the supervoxels. So higher the overlap, more likely it is that it is an action. Next, we use a saliency approach that gives us a cue that what are the most salient regions. So these saliency scores are accumulated for each supervoxel. That gives us that these are the supervoxel regions that are more salient, more observable for a particular action. And lastly, we have this motion boundary, which we use this optical flow to define where the motion is happening in this video. And that is a significant cue because all these actions have some motion involved in this video. Next, we look at knapsack weight. So I'd earlier defined that for each particular knapsack, we have a total weight that we want to restrict the action to be within. So for this particular case, we define the knapsack weight, which is theta, which is an accumulation of the average bounding box size in each frame over time for all those frames. So that tells us that the average bounding box size, when accumulated, is roughly the amount of volume that the action should be within. And the action selected, the supervoxel selected, shouldn't exceed that amount. So that gives us a way to restrict or constrain this problem. So the way that we define the directed acyclic graph, as I mentioned earlier, is that we have 2 dummy nodes, and then we define these directed edges from the start till the end of the video based on their temporal connectedness or the temporal overlap from start till the end. Next, we define the temporal constraint, which is shown over here. The key idea I can show over here is that the temporal constraints tells us that, let's say we are to select node number 7. So the temporal constraint would say that select node number 7 only if one of its temporal predecessors are selected, which says that select 7 if either 5 or 6 is selected, and select 5 if at least 1, 2, or 3, or 4 is selected. That ensures that we have a contiguous set of supervoxels selected, and that gives us a one continuous annotation in this case. So the knapsack formulation goes something like this, where we use binary integer linear program, and as I mentioned, that we want to maximize the value. So here u is the binary variable for each supervoxel node, pi is the knapsack value. We want to maximize the total value, and we are constrained with the weight, knapsack weight for each item, which is theta, and we want this to be under the total weight as defined. Alongside that, we have 2 dummy variables which we want to be selected at all times so that we have action from starting till the end. And lastly, we have these temporal constraints defined for this problem. Now, as I mentioned, that this would give us an action annotation for the training videos. However, we repeat this process for several action annotations for each video because we can have multiple actions. However, if we have those labels from clustering and the annotations from Knapsack, we can use them together to learn an action detector and use it in testing videos. However, we need to make sure that all these annotations truly belong to the action itself. So there might be some false positives or some people in the background that could be selected based on this Knapsack approach. So to make sure that we select good annotations for Knapsack, we come with a joint annotation selection approach, where we use all the annotations in the training cluster, and then we come with a similarity metric that looks at this quadratic programming approach, and P is the prior, U is the similarity. And then we want to select such that we only select one annotation that is truly similar within all the videos within a cluster. And that gives us good annotations to train our action detector or classifier. So for our unsupervised action localizations, once we have automatically discovered these video labels using clustering and bounding box annotations through Knapsack, then we can train an SVM classifier for action to recognize them in testing videos. And then for localizing, we use a similar Knapsack approach where we divide the testing video into supervoxels. We apply the binary integer linear program approach to select the action location and then classify using this SVM. For our experiments, For action discovery, we tested on these 5 data sets: UCF Sports, JHMDB, sub-JHMDB, 2MOS13, and finally UCF 101, which is 101 action classes. Next, we test our localization approach on 4 data sets, as shown over here. So first, I'll go through the experimental setup. So for features, we used 3D deep learning features for action discovery, where we use those deep learning features to come with a similarity metric and improve those clustering. We also use IDTF features for action localization that extract those dense trajectory features within each supervoxel to come with a localization. For evaluation on action discovery, we use the percentage of clustering accuracy, and for localization, we use the same metric that we showed earlier, which is the ROC and AUC curves. So for action discovery, we test our approach and we compare it to several known clustering approaches, as well as the state-of-the-art action clustering method, which is dual assignment k-means clustering. And first, we show results on UCF Sports, where we compare based on 2 features, dense trajectory as well as C3D. And here we show that we improve the clustering accuracy as compared to these known methods, that's k-means, middoids, n-cuts, dominant sets, and so on. Next, we show results on sub-JHMDB, which has 12 actions, JHMDB with 21 actions, 2MOS13 with 24, and then lastly UCF 101. And each one of them we show that we improve the clustering based on our discriminative clustering approach based on dominant sets. Now, after we have discovered these labels, we want to evaluate how well have we annotated these actions using Knapsack approach. So we assume that we have the perfect labels for each video, and we perform a weekly supervised action localization, where we say we have all these labels, we want to just measure the performance of the annotation itself. So for that, we test on UCF Sports. Here are some results on the first five actions of UCF Sports, and here are the next 5. And on average, we get an improvement of 6% that shows that the annotation of the Knapsack approach really works and gives us a better localization or annotation in this case. Here are some qualitative results on UCF Sports, where again, the action detected or localized is shown by the yellow contour, and the ground truth is by the green bounding box. Next, we show results on sub-JHMDB. So selecting those supervoxels and making sure that we have those temporal constraints really makes a difference, and we can see from the start and the end, we really have a localization for each action. Next, we have results on JHMDB with 21 actions. And lastly, on 2MOS13, which is, again, one of the most challenging data sets there is. Now, for our quantitative analysis on UCF Sports, we want to measure the localization performance. So since we are the first to come up with an unsupervised action localization approach, we compare it to other supervised methods. So here on UCF Sports, we compute the area under the ROC curve and compare it with the state-of-the-art methods, and our curve shown by the red curve over here. And here you can observe that we perform better than some of the supervised action localization method, which gives us good encouragement that this method really works, and we're able to better perform these annotations and clustering. Next, we show results on sub-JHMDB. So we perform competitive to the state-of-the-art. However, we also have a supervised baseline shown by the black curve, and here we perform better than most of the overlap thresholds shown on this data set. Next, we show results on sub-JHMDB. Here, our proposal again is shown by the red curve. We perform competitive to state-of-the-art, and then significantly better compared to the supervised baseline on multiple thresholds. And lastly, on 2MOS13, where we perform better again on all those on the supervised baseline approach. Now, since our method had a number of components to it, we want to measure the contribution of each one of those components. So for the first part, we measure how well the annotation selection, the joint annotation selection, helps in localizing the action. So here we show the comparison of selection through quadratic programming with and without, and we show that we significantly improve by selecting good annotations to train our action detector and be able to classify in testing videos. Here's an analysis on the different knapsack values that we use for our approach. So here we have the motion boundary, the saliency and humaness, and we show the performance individually as well as a combination, and we get a significant improvement when we combine all of those approaches. So in summary, we propose a new problem of unsupervised action localization We discovered these action classes automatically, and then we also use Knapsack to annotate as well as localize actions in testing videos. So the conclusion of this dissertation is that in the first part, we proposed an efficient way to localize actions in a supervised manner. Next, we proposed online localization of actions and interactions. And lastly, we proposed a new problem of unsupervised action localization. So for future work, there could be a number of problems that you can explore. So for online action localization, currently we predict and detect the action in the current frame. However, we can try to predict how the action would unfold in the future frame, such that can be used to deter or to set an alarm in surveillance videos. That could be really helpful. And there could be possible ways to explore that, such as deep learning-based generative models that can construct those feature frames and be able to tell what the action would look like in future. For unsupervised action localization, the current method assumes the number of action classes that are known to our method, and also we assume that each video belongs to a particular action to one of those K classes. So a future way to explore is that we can look at noisy videos where we don't necessarily have K actions. Some of them might be outliers, so we can come with a way to remove those, or we can come with a way that can explore and find out the actual number of classes without knowing in advance. So here are my publications throughout my PhD, and we also have a patent. Thank you.